aqueous solution is one in which water is the dissolving medium, or like the solvent. Water is a very, very effective solvent for ionic compounds. However, most molecular compounds, when they are put in water, and molecules remain intact. Two electrolyte categories. We have a strong electrolyte and we have a weak electrolyte. Strong electrolytes exist in the solution almost entirely as ions. Weak electrolytes, however, exist in a solution mostly as molecules. There are three types of aqueous reactions I'm going to talk about. One is a precipitation reaction, which the result is the formation of an insoluble product known as a precipitate. Now, there are some basic rules to show whether a substance is soluble in a reaction. Acid-base reaction. An acid is a substance that ionizes in an aqueous solution to form hydrogen ions. A base, on the other hand, is a substance that will accept hydrogen ions and or produce hydroxide ions in a solution. Both can be strong or weak. If it ionizes completely in the solution, it's strong. However, if it only partially ionizes in the solution, it's generally considered to be weak. With ionic substances, it's always going to be a strong electrolyte. However, with molecular substances, a strong acid will always be a strong electrolyte. A weak acid or a weak base will be a weak electrolyte. So, when we take an acidic solution and mix it with a basic solution, we get a neutralization reaction. Generally, this reaction will produce water and a salt, oxidation-reduction reaction, or a redox reaction. This reaction is when electrons are transferred from one substance to another. Now, when a substance loses electrons, that's called oxidation. When a substance gains electrons, that's called reduction. To keep track of moving electrons in a redox reaction, we assign oxidation numbers to the elements, atoms, compounds in the reaction. Atoms in their elemental form will always have an oxidation number of 0. Monatomic ions will have the oxidation number that is same to their charge. K+ will have an oxidation number of +1. For nonmetals, the oxidation number is usually negative. Fluorine will always have an oxidation number of -1, and hydrogen will have an oxidation number of -1 when it's bonded to metals, +1 when it's bonded to nonmetal. If you have a neutral compound without a charge, the sum of all these oxidation numbers will be 0. If the compound has a charge, the sum of the numbers is equal to that charge. In a displacement reaction, when a metal reacts with an acid or a salt, one of the compounds in the reaction is oxidized.
For instance, if we react magnesium with hydrochloric acid, we get magnesium chloride and hydrogen gas. And in this reaction, we see that the magnesium, which previously had an oxidation number of 0, has changed to have an oxidation number of +2. And the hydrogen, which had a previous oxidation number of +1, has gained the electrons and has an oxidation number of 0 now.
In order to tell whether a certain metal will be able to be oxidized, we use what's called the activity series, which is just a list of elements. So in the activity series, any metal can be oxidized by any element below it in that chart. It's important to know the concentrations because the behavior of the solutes often depends on that. To express concentration, we use the term molarity. A 1 molar solution of NaCl is 1 mole of salt per liter of water. If the concentration in the water is too high, you can dilute it with a pretty easy chemical equation, which is displayed on the face. The equation is the moles of the concentrated substance times the volume of the concentrated substance equals the moles of the desired dilution times the volume that you want for the desired dilution. If the concentration of a solute in a solution is unknown, you can use titration. You take a specifically known concentration and you add it to the unknown until you reach the equivalence point. The indicator will change colors and let you know. To understand electronic structure, we first need to talk about light. All types of electromagnetic radiation carries energy. All the types of radiation travel through a vacuum at a certain speed called light speed. They all have a wavelength and a frequency, which is the number of wavelengths that pass through a given point in 1 second. And these two things, the wavelength and frequency, are inversely related. Now we're going to talk about some people who made important discoveries to our current understanding of light and electronic configuration. Planck said that energy could be absorbed or emitted in chunks called quantums. Einstein expanded on this theory when he said that light travels in packets called photons. Niels Bohr used these two theories to explain the line spectra. When radiation is split into wavelength components, a spectra is produced for a range of colors. And it was found that certain gases under reduced pressure with a high voltage passed through them emitted a specific color. And this color, when it was passed through a prism, created specific colors in the spectra, but not all of them, which is called the line spectra. So to explain this, Bohr assumed that electrons moved in a circular pattern around the nucleus and came up with three postulates. One, that only orbits of certain radii, corresponding to certain definite energies, are permitted for the electron. 2, an electron in a permitted orbit has a specific energy. And 3, energy is emitted or absorbed as a photon by the electron as it goes from one energy state to another. He then said that the existence of these spectral lines was because of the quantized jumps of the electrons from different energy levels. However, this theory only works with hydrogen, so it is incorrect. Louis de Broglie suggested that electrons have a wavelength characteristic found with this equation, and this was later found to apply to all matter. Heisenberg created the uncertainty principle, which says that we cannot know the exact momentum and location of an electron in an atom at the same time. Schrödinger created the model quantum mechanics, the same model that we currently use today. This model uses orbitals, which describes the specific distribution of electron densities, or where the electrons are most likely going to be at, to describe electron location in an atom. And these orbitals therefore have a specific energy and shape. So this model uses 3 quantum numbers to describe each orbital. The first number it uses is the principal quantum number, or n. As it increases, the orbital becomes larger and the electrons spend more time farther from the nucleus. The second number, the azimuthal quantum number, L, can value from 0 to n-1, and it defines the orbital shape. The third number, the magnetic quantum number, or m subscript L, can value from -L to L, and it describes the orbital orientation in space. The 1s orbital is represented with a sphere, and this sphere shows where the electrons are most likely to reside. For p orbitals, the region where we're most likely to find electrons is dumbbell-shaped, and starting at n equals 2, for each shell, there are 3 p orbitals. When n is 3 or greater, we get 5 d orbitals, as shown here. Once we get to n equals 4 and on, there are 7 f orbitals. The energies of these orbitals increase with n, so the 3p orbital has more energy than a 2p orbital would. 2 Dutch physicists discovered that there was actually a 4th quantum number, m subscript s, the quantum spin number, when they postulated that electrons spin in 2 different directions on an axis. Pauli then used this discovery to create the Pauli exclusion principle. This principle says that no 2 electrons can share the same 4 quantum numbers in one atom electron configuration. Because electrons always try to be in the lowest possible energy states, or ground states, we fill the orbitals in order of increasing energy. We can represent these electrons' configurations by writing the symbol for the occupied subshell, followed by a superscript number indicating the amount of electrons in that subshell. We can also use an orbital diagram as shown here, which shows electron spin. Hund's rule states that electrons will occupy orbitals singly to the maximum extent possible. So in order to write electron configurations in a simpler manner, in one that takes up less space, we use abbreviations. For example, the electron configuration of potassium is commonly written as argon 4s1. So this pattern is basically followed for all the rest of the elements, and the periodic table shown here will give you the electron configuration of all of the elements. There are, however, a few electron configurations that don't seem to fill in a predicted manner, like chromium. This is simply because of the closeness of the 3d and 4s orbital energies. Alright, so there are 3 types of chemical bonding: ionic, covalent, and metallic. Ionic is when an electron is transferred between 2 atoms and the charges hold the atoms together. Covalent is when a shared electron holds the atoms together, and metallic, when each atom is bonded to several neighboring atoms and the electrons can flow freely through the metallic substance. Valence electrons are the ones used in chemical bonding and are most often in the outer shell and can be shown using a Lewis structure. The octet rule says that atoms will gain, lose, or share electrons until they are surrounded by 8 valence electrons. Ionic bonding. The formation of ionic substances is exothermic and it stabilizes the atoms. The extent of this is measured in lattice energy, which increases as the charges on ions increases and as their radii decreases. Electrons are most easily added or subtracted from the valence shell, so adding or subtracting them from a new or inner shell is energetically unfavorable and very rarely happens. However, for transition metals, the valence s electrons are lost first, then as many d electrons as are required to reach the charge. Covalent bonding. In this bonding, the atoms are held together by the electron nucleus attraction. This can be represented with a Lewis structure, as shown, where one line is one shared pair of electrons, 2 lines is 2 shared pair of electrons, and 3 lines is 3 shared pair of electrons. In a nonpolar covalent bond, the electrons are shared equally. However, in a polar covalent bond, one atom attracts the electrons more greatly than the other atom. We use electronegativity, shown here, to determine which covalent bond it will be. The greater the difference in electronegativity between the two atoms, the more polar the bond. We measure polarity with dipole movements using the equation here, where Q is the equal but opposite charges on each atom, and R is the distance at which they are separated. At times, more than one Lewis structure can be used to represent a molecule. When this happens, we use the structure that has the formal charges closest to 0. Formal charge is the valence electrons in an isolated atom minus the valence electrons in the atom in the compound. Sometimes, more than one Lewis structure is required to show the accurate arrangement of electrons. When this happens, a resonance structure is used, which shows that the accurate representation of electrons is actually an average. The octet rule applies to most bonds, but it fails when the molecules contain an odd number of electrons, when an atom contains less than an octet of valence electrons, or when an atom contains more than an octet of valence electrons. The strength of covalent bonds is determined by the energy required to break that bond, or the bond enthalpy. The higher the bond enthalpy, the stronger the bond. In general, as the number of bonds between two atoms increases, the bond grows shorter and stronger. Those are the basic concepts of chemical bonding.